Thank you so much for inviting me. I'm really honored to be able to give this keynote at this conference that I've been going to for over a decade. So what I want to focus on in this talk is, having been in academia for a long time and now being in the startup world for about 2.5 years, one constant in my life through all of these different things that I've been doing over this time has been technology transfer and building systems that people use. So what I want to focus on in this talk is tell you about some research projects that I've worked on, give you kind of the post-mortem on what happened with these, and then give some thoughts on what I think we can do as a community to help our community make an impact with the technology that we're designing here. Okay, so I think that one thing that's really interesting, here we are standing in 2020, and I don't have to tell anyone here that InfoSec is becoming critical to everything. I think a lot of the people in this room would probably be surprised to see the extent to which, 15 years ago, what we might have thought of as InfoSec and what we think of it now has broadened so dramatically. So, we live in these interesting times where the work we're doing is critically important to the world, right? And we all know that. And so, it should be the case that in this brave new world that we live in, where everything that people touch is affected by computers, and what we do is make sure those computers don't break and harm people, our work should be critical. It should be easy for people to be convinced to take the ideas that come out of this community and to adopt them in practice. And that's the way the world should work. But in practice, we all know that that's not the way the world works. I think we know that because we celebrate when our research actually gets used and doesn't sort of fall by the wayside because we missed something or it didn't get adopted or whatever it is. So what I want to talk about in this talk is tech transfer. What can we do as a community to make it easier and better for our community to be aligned to produce research that will really get used? And I'm going to be focusing just on building systems in this talk because I think we've done an excellent job in developing, the ability to break a lot of systems and to go to industry and to get them to patch. I don't think that's where we need to improve. I think what we need to improve is how we think about actually building systems and making people use them, convincing people to use them, which is, I think, why we're all here in the first place. Okay, so given that InfoSec is so important, why is tech transfer so hard? I think we all know this. So tech transfer is hard because no one notices security until it stops working, right? And so really what InfoSec is there to do is to prevent catastrophic events, catastrophic failures. It's very hard to get people to invest in security when they don't see this black swan event that you're warning them against happening any day soon. Of course, when it does happen, it would be a problem, but they don't see it. It's hard to get them to invest. And as an aside, as someone who's writing a cybersecurity startup, we always have to tell the story of something beyond security as what we're selling, not just as security itself. Okay, so if security is supposed to prevent catastrophic failures, we have another problem, which is often when these catastrophic failures happen, it's the implications or the repercussions on the party that should have been securing their system is actually not very big, right? So for me, the most striking example, I don't know how many of you are familiar with the Marriott data breach. Anyone read about that? So this is a fascinating case. So we have the data of 400 million people getting compromised due to the negligence of Marriott. Okay, so the implications on all those people is their data was compromised by who knows who. What was the implications on Marriott? Well, Marriott had cyber insurance, and that insurance covered all the damages that resulted from this issue, and as a result, they paid $3 million. Okay, so $3 million for a company like Marriott is pocket change, right? It's maybe what it costs to run maybe 1 or 2 hotels. It's nothing. So why should they be investing in security when the repercussions are so little? And we have to contend with this. I personally, this is a digression. I personally don't believe that this is going to stand for much longer because if you look at other industries, this doesn't happen. But this is where we are today. Tech transfer is also hard because we are almost always backporting security into existing systems. And this is not a bad thing. This actually makes sense, right? We don't design every system that's used in the world in this community, but then what we do is go look at the systems that are being successfully used. We see how they're being used, and we ask ourselves, where are the vulnerabilities here, and can we fix them? Right, so what we're often doing is coming into a system that's existing, that's important, that's why we're paying attention to it, that's getting used in all kinds of ways that we may not understand, and we say, okay, now we need to secure this, so please, do all these things that we want you to do. And so this is where we get these problems. So given that we're against these odds, and I don't want to paint a black picture here, but this is a reality, this is where we are, the odds are against us. What can we do as a community, as an academic research community, to improve the chances that our technology actually gets adopted, given that we're up against these odds? And so I have 2 ideas that I'd like to propose in this talk, and so the rest of this talk will be a research talk, but I'm just standing on my soapbox now that I will shortly get off. The first one is integration. So one of the key things that we think about when we do InfoSec research is what can we secure? How can we make it more secure? But maybe we don't necessarily think about how easy it is to deploy, how easy it is to plug into the system. And what I found with my own research is that often when you start out on a research problem, you don't really understand like how your solution actually fits in and all the different things that your solution may be breaking. And in fact, what I'm going to be doing in this talk is tell you about a story that happened to us where we actually, as we were trying to get our technology adopted, it started breaking all these other things that were being developed at the same time that we were working on it. So we couldn't have even foreseen the difficulty of integration when we started the project. And this is all good, because I actually think that if we knew how difficult things were when we started the research project, we maybe would never start. But at the same time, I think as a community, we need to encourage ourselves to sort of walk down this long path of integration and figure out the right way to maneuver our solution into the system that we're studying. This takes time. The next item that I want to really push is specification. So for me, when I say specification, I mean standardization, so internet standards. Well, the goal here is that an independent implementer can reproduce what you did. And so one way we can do this is by releasing open source code. Another way we can do this is by actually standardizing what we're doing. I personally am a big fan of standardization, and so I think all of the results that I'm going to be talking about here come from either like actually going to a standards body and trying to get something standardized, or writing that level of specification down as part of our papers, which we just decided to do for our own sake. No one really wanted us to do that. So my soapbox is let's think about these things and let's give ourselves the time to work through all these issues. This isn't necessarily what we initially start with when we think about research, but I think it has a really big impact on the success of the research, and I hope I can convince you with some of my own adventures that I want to tell you about. Okay, so my first adventure is an adventure that we've been on since around 2013. We have been looking at a problem with privacy in the domain name system security extensions, DNSSEC. So we started there. And as part of that work, we had to develop a cryptographic primitive called a VRF, a verifiable random function. So we started with a DNSSEC privacy problem. We worked on that. We came up with a spec. We then ended up developing a verifiable random function, came up with a spec for that, and then this thing actually took off, and we found it being used in a whole bunch of other places like that we weren't expecting, like authenticated data structures and actually proof-of-stake blockchains. So the technology that I'm about to tell you about is used in Algorand and Libra, which is the blockchain that Facebook put out, if you noticed last year. So this actually ended up being used here, completely unexpected to us when we started this project. And a lot of that has to do with the two questions that I mentioned, how difficult it is to integrate the technology and how well is it specified. The second adventure that I want to tell about is very short. This was sort of like the most beautiful case where everything fit into its, the pieces fit in place very easily. We came up with a protocol for certifying the correctness of public keys. We wrote down the spec, we did some open source implementation, and then it was adopted into a couple of different projects and companies. So Unbound and Zengo are both doing multi-party computation for ECDSA keys, and this is used either for reducing risk when you have key storage and also for cryptocurrency wallets. And this was just sort of picked up again without us really doing anything. So I'm going to start with adventure number one, and let me tell you the adventure. And one fun thing about giving a keynote rather than a conference talk is I don't have to sell you on the solution. I can really tell you the truth about what happened and all the things that went badly and went wrong. And so that's what I'm going to have fun doing right now, telling you about this story that we went on. Okay, so in 2012, I was teaching a class at BU. I was teaching about DNSSEC, and I discovered there's a privacy problem with the DNSSEC, and I became obsessed with it. This is me personally bothering everyone I know to come up with a solution. In 2014, we were able to propose a solution called NSEC5 to this privacy problem. 2015, we went to the Internet Engineering Task Force, which is, actually, and I think this was published at NDSS. In 2015, we went to the Internet Engineering Task Force with a draft specification of our solution. We were very excited about it, but they hated it, and the reason they hated it was because it was based on a crypto system, RSA. And DNS community was over RSA, did not want to build anything on top of RSA, and said, come back to us when you have something that uses modern cryptography like elliptic curves. So we did. 2017, we came up with a version of NSEC5 based on elliptic curves. To do that, we had to design a verifiable random function based on elliptic curves. So we went with that to the IETF. And then what we were told was, that's very nice, but we can't read your spec because your spec has all this crypto in it and all this DNS in it, and no one understands it. So we broke it into two parts, the crypto part and the DNS part. And so we did that. And then now that we had the crypto part, the VRF part, we started meeting all these people who were interested in using VRFs. So in 2017, we were talking to a bunch of different teams. There was one from Yahoo and one from Google, using the VRFs, using VRFs that they had sort of implemented based on a research paper that they found. And these actually VRFs were completely broken, completely insecure. We found that they were insecure, suggested they use our spec. And then after that, this Algorand paper came out. Algorand is a proof-of-stake blockchain protocol that is built around VRF, so they needed a secure VRF, so they ended up using our standard for their implementation, and that's what's being used now in Algorand. And then after the Algorand paper came out, a whole bunch of other blockchains came out using VRFs as well, and all of that, many of those are also using our VRFs. So now we have all these independent implementations of our VRF that have basically been built by all these different blockchain teams, and I'm going to show you that later in the talk. So meanwhile, all this is happening. We're doing all this exciting adoption in the blockchain space, which, by the way, is what my startup is on too, so I'm very excited about that. But unfortunately, we didn't make as much headway with the DNSSEC solution that we had as we'd hoped, and I'm going to tell you a little bit about some of the problems we ran into in getting to that, getting that adoption done. Okay, so that's the story. And now I'm going to tell you some actual details, okay? So let's start with what is a VRF. I'm going to explain what a VRF is. I think generally it's a very cool primitive, so hopefully someone in this room thinks about it and ends up putting it in some other new application that we haven't thought of yet. I'll tell you a little bit about our elliptic curve VRF specification, and then I'll talk about the two applications. The one we started with, which is NSEC5, which is actually an authenticated data structure, and the blockchain application, which is Algorand, which I wasn't involved in at all. I'm just showing it as an application. Okay, so what's a VRF? A VRF is a hash function. We all know about hash functions. There are different kinds of hash functions that we know. We have unkeyed hash functions, like SHA-256, right? And then we also have keyed hash functions, which we call pseudorandom functions, like HMAC. Right? When we have a pseudorandom function, you cannot compute the output of the hash if you don't know the key. When you have a regular hash function, anyone can compute the hash. That's simple. So what's a VRF? A VRF is just the public key crypto version of a pseudorandom function. Okay, so instead of having a symmetric key, we now have a public-private key pair. When we are going to compute the hash, what we do is we use the secret key to compute the hash. This is very much like a PRF. But now we have an extra thing here, which is the verify step. We have this public key, and our public key can be used to verify that the hash was computed correctly. Okay, so in a PRF, we can't verify that the hash is correct. In a VRF, we can. V for verify. Okay, so that is a VRF. These were proposed in 1999 by Micali, Rabin, and Badhan. And they have a couple of properties, so let's see how they work. So we have here our prover and our verifier. Our prover has the secret key. The verifier has the public key, and they're going to be hashing this input. So only the prover can compute the hash because only the prover knows the secret key, right? So the prover will get the input. It will compute this value called the proof, which is computed using the secret key. Then it will send that over to the verifier. The verifier can verify that the proof is correct using the public key. If it is, it can transform this proof value into the hash. And that's the hash value that we use in the VRF. It can transform the proof into the hash, and then if the public key tells you that the proof is incorrect, then it'll just output invalid, and there's no output of the hash. So the properties that this have are just like a regular hash function. So this idea of uniqueness, so every input has a single hash value. This is the same thing we have in SHA-256. When you hash something in SHA-256, there's only one output you can get. Same thing with a VRF. Similarly, collision resistance, it's hard to find two inputs with the same hash. Okay, so VRF has the properties of a hash function. It also has the properties of a pseudorandom hash function. So in the pseudorandom hash function use case, what we do is we take the input, we give it to the prover hashes it to get, the prover constructs the proof using the secret key, then it constructs the hash using this transformation proof to hash, which is a public transformation, no keys involved, and sends only the hash over to the verifier. Right? So in the use case where you're only getting the hash but not the proof, you actually cannot tell, this thing looks completely pseudorandom to you. So in other words, if you don't know the proof, it's impossible to tell that the hash corresponds to a particular input. This is the same idea that you have in a PRF, right? You can't compute the output of the PRF if you don't know the secret key. Same idea here. So if you don't know the proof, it works like a PRF. If you do know the proof, it works like a hash. Okay? So that's what we do with the VRF, and now I can show you what our VRF looks like. So our VRF was born because we went to the DNS op working group with NSEC5 based on RSA, and they said, build NSEC5 based on elliptic curves. And so in order to do that, we needed an elliptic curve VRF. So this is the elliptic curve VRF that we developed. This is a high-level explanation of how it works. So we have the secret key, which is this value here, this exponent value. We have the public key, which is g to the exponent, g to the secret key. Okay? So in order to, and now all of these points here, these are points on a curve. This G is the generator of the curve, and this group here is the elliptic curve group that we would be using. So for example, ED25519 or the NIST P256 curve. So this is the setup. I need to show you how to compute the proof. So the first step is to take this input and convert it into a curve point. So you have this hash function. This is just a transformation that converts this input into a curve point. We get a curve point H. We raise it to the secret key, and this gives us a value gamma. Okay, so this gamma is just this input raised to this input transformed onto the elliptic curve, raised to the secret key. So we send this gamma over as part of the VRF proof, along with two other values, C and S. So what are C and S? C and S are a zero-knowledge proof that gamma is actually h to the x. Okay, so all we're doing is we're sending this h to the x over here, and a proof that this really is h to the x. The reason this is a zero-knowledge proof, because we have to do this without actually revealing x. Okay, so that is what we send over as part of the VRF proof. How do we actually verify that the proof is correct? Well, what we do is we check that this is a valid zero-knowledge proof. So if the C and S actually do prove what they're supposed to prove, then all we do is we take this gamma and compute an actual hash over it, like SHA-256, and that gives us the output of the hash. Okay, so that's our VRF at very, very high level. And it has the properties that it needs to have. So what is the first property? Pseudo-randomness. Pseudo-randomness means that if you don't know the secret key, you cannot generate the value of the hash by yourself. So that's pretty easy to see. The reason for that is because this is h to the x, and if you don't know the secret key, it's very hard to compute gamma. Right? If you don't know the secret key x, you can't compute gamma, you can't compute this hash, and so it's hard to compute the hash without knowing the secret key. The second property is uniqueness. So uniqueness requires that there must be a mapping, a one-to-one mapping from the input to this hash over here. Okay, why is that the case? Well, we know that gamma, because of this proof, because this C to S tells us that gamma is equal to h of x. Right? And so there's only one value, which actually is h of x. That's the value h to the power of x. And so that is actually what our output is based on. And so we have uniqueness. Right? So again, follows from the fact that this is h of x. We know it's h to the x, and so it's correct. Okay, so that is like the 1,000-foot view of our elliptic curve VRF. This is what it actually looks like. So all the stuff that I'm showing here is really just showing you how we computed this C and S. Okay, so for those who care, this is a Chom-Penderson discrete log inequality proof with Fiat-Shamir applied to it. So that's how we compute this. So what did we actually do? So what's interesting about this work and frustrating for me about this work was that a VRF based on this approach actually appeared before we did our research. And actually, we didn't know about it, by the way, but it was prior to our work. There was a VRF that used this same type of approach to be a VRF, but there was no proof of security, and there was actually a fatal flaw in that VRF, which was that this hash value here, this is part of computing this C, which is the proof. So we have to do this thing over here. If you put the wrong values in here, it's a total disaster. The security of the scheme completely goes out the window. And we've seen countless examples of implementations that put the wrong values in here, and they're insecure. Actually, we were emailed just this week by someone who had this flaw in their VRF that wasn't using our spec. So one of the things we did was actually make sure it's correct. There's a lot of places where this stuff can go wrong. We had a security proof. As part of our security proof, we were able to actually really optimize this design. One of the things we wanted to do was to have very short proofs. The reason for short proofs is because we were sending them in the DNS response, and we didn't want big things in the DNS response because that's terrible for DNS. So we tried to squeeze this down, and we were able to do that, and we got away with it because we had a full crypto proof that this actually worked. And then we get into like specking all the things. So for instance, we need to choose a nonce. How should we choose a nonce? We spec the way to choose the nonce. We have to hash this value to a curve, right? This is just like a scalar. We need to turn it into a curve point. How do we do that? So we determined which hash to curve algorithms we could use and included that in the spec. We made sure that this worked with all the elliptic curves that we were interested in. So currently it's spec'd for the NIST P256 curve and the ED25519 curve. We've had some interest in doing this for the Bitcoin curve, but we have not yet done that, the SEC P256K1. And so there's a lot of stuff we had to do. And it was fun. It was fun for us, but we didn't get much credit for it in the academic community. But this was really fun, and we actually have this fantastic stack that you can look at that was adopted by the Crypto Forum research group at the ITF. So we did this. I think we dropped the spec around 2017. This is a list of the implementations that are out there that use our VRF. This list is the ones that are actually compliant with the spec as it is now. These are some outdated implementations that used earlier versions, and you can see who's using this. A lot of this is blockchain stuff. This is key transparency, which was sort of the earlier thing that started picking up the VRF, but got picked up by a lot of different blockchain projects. So I'm pretty excited about this. But I want to now tell you sort of the less exciting part of the story is like what happened with the DNSSEC proposal that we had that sort of drove all this research. So okay, so NSEC 5, one way of looking at it, because I don't want to spend too much time talking about it, is it's an authenticated data structure. So what we have is we have a data structure, it's authenticated, it's pre-computed, and it's stored. For those DNS experts in the room, basically we have this thing stored in the name server, right? And the idea of NSEC 5 and the idea of sort of all of this stuff that I'm about to put on here, all of these different applications, is that instead of doing an authenticated data structure using hashes, like a Merkle tree that we're all familiar with, we're going to actually use the VRF as the hash instead. And that gives you some pretty nice privacy properties, and that's really what we did for NSEC 5. We took away hashes and we replaced them with VRFs, and that gave us what we wanted. Okay, so at a high level, that's what we did here. Let me explain to you why authenticated data structures matter, why VRFs matter for authenticated data structures. So here's an authenticated data structure. We have our prover. He's got this data structure that is pre-computed and stored at the prover, and then the verifier has the root of the data structure. Right? And the idea is that the verifier should be able to send a query to the prover saying like, hey, is this thing in the data structure? And the prover will be able to say, yes, here's a proof, or no, here's a proof, it's not, or yes, here's a proof that it is. And so, most of us are familiar with Merkle trees. Usually this proof takes the form of like a path up to the root of the Merkle tree. That's one application that you might see. With NSEC, it's actually just the bottom part of the Merkle tree without the top. But anyway, it's the same idea. You send some sort of proof over that something is in the data structure, and the verifier can check that this proof corresponds to the root of the data structure that they have. Okay? So that's the idea behind authenticated data structures. So what's the problem with this approach? The problem is that this data structure is just based on hashes. And so this can be vulnerable to dictionary attacks. So the idea is, what is a dictionary attack here? The idea would be instead of sending queries to the prover in order to figure out if something is in the data structure, with a dictionary attack, you can just figure it out on your own without ever asking the prover. Okay, so that's the problem that these things have. And this is the problem that VRFs are going to solve. The reason that this is a problem is because it prevents the prover from potentially doing access control on the verifier. It can't control what information it provides to the verifier. In the context of DNS, the reason that this was a problem, the whole story started in around 2005 when DNS sort of specified basically an authenticated data structure to solve the integrity problem for DNS. When that was specified, someone noticed that there was this enumeration problem where you could actually figure out what names are in the zone or what data is in the data structure without actually sending any queries. Right? So this was viewed as a problem. A whole bunch of research came out to try to solve this problem. DNSSEC ended up with NSEC 3 as the solution, and unfortunately, it's still vulnerable to this attack. Right? So. This issue was actually something that was significant enough to cause DNSSEC to be redesigned. And so what we observed separately, without showing you the full NSEC 5 solution, is our observation, independently of all these other observations that I showed before, is that you could store the VRF hashes of the data instead of the actual data. So the idea would be, instead of having the data structure hash the data up to the root, what we would do is first store a VRF hash, and then we could hash that up to the root. Okay? So why does that actually solve our problem? Well, the idea is that in order to compute VRF hashes, you need a secret key. right? That's how we compute VRF hashes. So if you don't have the secret key, you can't compute VRF hashes. So if you can't compute VRF hashes, you can't check what's in this data structure unless you actually ask the prover a question to compute the VRF for you. Okay, so that's the goal of the VRF. The VRF forces you to send every question to the prover and not answer questions yourself. And this limits this type of enumeration problem that we were seeing in these different use cases. Okay, so that's what pseudorandomness does. Now, the reason we actually need a VRF for this is because we also need uniqueness, right? If this was done using just a pseudorandom function, like a regular keyed cryptographic hash, the prover could lie about what's in the data structure. It could just make up what's in the data structure and put whatever it wants, because you have no idea what the keyed hash value computed on something if you don't know what the key is. Right? So what we need to have is we need to make sure that we actually believe this prover and that he doesn't lie about what's in the data structure. And the way we do that is with the VRF. So VRF uniqueness ensures that the prover can't claim that something is in the data structure when it's not, because if he did that, he would be sending a proof that was incorrect. Right? The proof would be false. So by combining these properties, VRF uniqueness and VRF pseudorandomness, we can get the same type of guarantees that we had in authenticated data structures, but just by throwing in this VRF, we remove the enumeration problem. Okay, so that's sort of the general story of like why VRFs are useful for authenticated data structures. So, you know, we had our NSEC5, which is like a version of this, and we went to the IETF with it, and then what happened? So the first thing that happened, which is really interesting, is that initially this idea of enumeration, that a party can actually determine what items are in the zone without actually querying for it, was viewed as a problem. That was the case in 2005 and 2008. But then, you know, time went on and enumeration started to be viewed as a feature rather than a bug. So the idea that you could tell what's in the zone without sending a query is actually pretty useful if you want to minimize the number of queries that you send, right? So at the same time that we came up with NSEC5, there was actually a proposal that said, hey, look, this is enumeration. Why don't we use it to minimize the number of queries we have to send? And that actually was adopted by the DNS working group the same time that we were coming with this proposal to stop enumeration. So you can see the problem here. And then the second idea is that these hash-based data structures are actually solving a problem, which is that we want to be able to, okay, so why do we have hash-based data structures in the first place? The idea is we don't want to be computing things on the fly. We don't trust the prover, right? We don't want to give him the keys to the information. We don't want him to give whatever answers he wants. We want to give him pre-computed information that he can use to answer questions and he can't cheat. Right? So this notion of pre-computation was critical to the design of NSEC5 because we thought pre-computation is really important. But as we were trying to get this used, actually it turned out that the community decided that pre-computation is maybe not so important, and now we want to do dynamic computation. And so all the work we did here with NSEC5 to support pre-computation was not really useful anymore because the community moved in a different direction. So this was one of these interesting things where I feel like we had solved the problem. Maybe if we'd come 10 years earlier, we would have had a lot more success. But I still think, you know, I can give a separate talk about why I still think NSEC5 is useful, but these are the hurdles that we encountered, and that's why I have a rock going up a hill, and we were not aware that this was going to happen when we started the research. So what's my message here? So my message here is that, you know, by going through this iterative process where we spent many years on this project, we had many versions of the project, we had like multiple papers that actually tried to propose different ways of doing NSEC5, and we hit different hurdles. We actually were able to kind of learn all of these things and actually end up with something that people did use, which is the VRF. So let me show you how actually our VRF is now being used. So in 2008 and 2007, the Algorand paper came out. Algorand is a proof-of-stake blockchain. What is a proof-of-stake blockchain? A proof-of-stake blockchain is there's all these nodes, and these guys are all going to compute together the blocks in the blockchain. This is a super high-level version of this protocol. So each one of these guys has a stake. So let's think of the stake as the number of coins that they have. Each one of them has a stake. So the amount of voting power on a block is proportional to the stake that the guy has, right? So if I have this many coins, I'm going to have this much voting power. That's the idea of a proof-of-stake blockchain. It's very different from how Bitcoin works, if that's what you're familiar with in your head. So in this case, you know, we have all these players. They each have their stake. The way they're going to decide if they get to contribute to the decision of what goes in a block is the following. So for every block, all of these guys learn a seed. So this is a public value that they all learn. They each take that seed, and using their secret key, they compute a proof using their VRFs. So this is a VRF proof computed with the seed as an input and their secret key. Okay. Next step is to compute a hash. So just convert the proof using proof to hash into a hash value. And then they see, is their hash actually indicative of them having the right to vote on this block? Okay? So the idea is all we're doing is we're saying if I own like 2% of the coins in this system, then if my hash is smaller than 2%, then I actually get my vote, and if it's bigger, then I don't. Okay? So it's just a way of weighting your vote. And so if your hash is small enough, you are elected to this committee. Okay, so we're basically using the VRF hash as a way to randomly flip a coin with probability proportional to the stake that you have in the protocol. All right, so now, what happens if you're elected? What you do is you actually send out the proof that you're elected, the VRF proof if you're elected. The remaining people in the system can use VRF verification to check that indeed your proof is actually correct, right? You would check that this proof is correct for the seed given the public key of this guy. If it is, then you will be allowed to choose the next block, and if not, you won't. So why are these things using VRFs? So there's a couple of reasons. So they're using VRF pseudorandomness, gives them the property that an adversary cannot predict who will be elected. Right? So you can't know what your VRF hash will be. Even if you know the seed, you don't know the secret key, so you can't predict the VRF hash. You can't predict if this guy will be elected for a given block. So that prevents DOS attacks on the parties that are elected to participate in the selection of the block. And then VRF uniqueness, this is the most important thing, right? This guy will always want to cheat and claim he's on the committee when he's not, because then he gets to influence the blocks. Right? So we want to make it impossible for him to cheat and claim he's on the committee if he's not, and that's VRF uniqueness. If his proof is actually invalid, then these guys won't let him be on the committee, right? So he can't cheat and claim he's on the committee when he's not. So we're using VRF uniqueness and VRF pseudorandomness, and this whole idea of proof of stake blockchains is very strongly tied to the notion of VRFs. So, the lesson here is that integration is hard in unpredictable ways, especially in this case for us, which was a case in which there was like a moving target as to how we understood the way the system worked and the way the community wanted the system to work. But by having this specification, it wasn't all lost. We ended up getting sort of a lot of use out of the VRF that we designed for DNSSEC in a place that we completely didn't expect. Okay, So great. So now that was sort of a really hard and tricky story that I sort of shrunk down into a few slides. I want to tell a much simpler story here, where everything was very easy. We weren't in this big hairy system like DNSSEC. We solved a very simple problem, and it ended up getting used pretty quickly after we solved it. So I'll just tell you briefly what the problem is. So we all know about public keys in crypto systems, and if the keys are chosen correctly, everything works well, right? Have you ever thought about how keys are chosen in crypto systems or who chooses them? So most people don't, actually. But it turns out that if you choose keys maliciously, if you have an adversary that's choosing public keys in a bad way, they can actually break the security of the crypto system because it's not going to work in the way that you expect. So this particular project started because we were using RSA keys in Tumblebit, which was a system we built for Bitcoin privacy, that we designed for Bitcoin privacy. And in our system, actually, if you chose the keys maliciously and incorrectly, then security completely broke down. You could steal money out of our system. You could steal Bitcoins. It was really bad. So we started to think about how do you actually correctly make sure that keys are correctly chosen. So let's look at what happens, what the problem looks like. So we have the secret key, which is over here. We have the public key. This is an RSA key. This is the RSA modulus. This is the encryption exponent. This is the decryption exponent. The way RSA works is that we take this message, we raise it to the power of D, and then go mod n. This is the RSA modulus, and we get this value sigma. And if we were to send a sigma over to this verifier over here, he could raise it to the power of E, mod n, and he would get this value m prime. Now, whenever we use the RSA crypto system, we're basically assuming that m prime and m are equal, right? We're assuming that RSA is a permutation. Right? So RSA is supposed to be a permutation. If everything's working properly, m prime will equal to m, and we're all good, and we can build signatures and encryption and whatever else we want to build out of RSA. But actually, RSA is not a permutation if you choose n and e in a malicious way. So there are ways to choose n and e such that actually this is not a permutation. M could either, there could be multiple values that actually map to the same sigma, and all sorts of terrible things start to happen if this is the case. So cryptographers have known about this problem for a long time. And if you look at some of the older papers from the previous decade, you'll see these trivial or folklore solutions being proposed. And what's interesting to me is that this is the type of thing that's often dealt with in the footnote of a paper. Like, by the way, we have to make sure the key's not maliciously chosen, because if it is, bad things will happen. Use these trivial solutions. So let's see these trivial solutions. So the first trivial solution is to just throw a GCD along with every one of these computations. So anytime I raise something to the power of e, I'm also going to do a GCD of the result with the modulus, and if it equals to 1, then I know everything is good and the RSA keys cannot be malicious. Right? If the RSA keys were malicious, I would see that there was a problem here, and I would be able to detect the problem with the RSA keys. So that seems fine. Here's another way we can do it. We can actually require that this E here has a set of properties, so we have to make sure that E is large and E is prime. Okay, so if we do that, then we don't have to worry about certification, everything is fine. Okay, so these are the folklore approaches that you find in papers. The problem is that these are both terrible approaches. So the first reason that this is terrible is because, RSA standard, if we look at the RSA standard does not say to do this. So if you actually wanted to take your RSA code and throw this GCD in here, what you're doing is you're going into RSA crypto code and putting something else inside, which I think most people here agree with me, like that's pretty terrifying, going in and changing someone RSA code. Not very desirable. So this is not very practical, at least in terms of from a software engineering perspective, and it's also not according to the way the RSA standard works. This approach is also terrible. And the reason it's terrible is because usually we choose very carefully these exponents to be small so that the RSA operations are fast, right? Because every time we do this, we have to raise something to an exponent. We very carefully pick these exponents. It used to be that E was even set to 3. That's less likely these days. But we choose these in very careful ways. So kind of choosing this giant E is very, very costly because we'd have to deal with it every time we do an exponent. So neither one of these solutions are viable. And so we came up with a solution like this, which is basically that anytime you send an RSA key over, you also send over this certification. And the certification guarantees to you that the keys are chosen correctly. So it's just a really simple idea. We don't have to change the RSA code. We just throw it on top, and you can use it to verify the keys are correct. And so just a couple of notes about the protocol. So when you receive the keys, you also receive the certification. It's sent just from the guy who chose the key to the recipient of the key. So basically from the prover to the verifier here, this party would send it over along with the key. It's non-interactive, which means it just gets sent over and we don't have to communicate back and forth. And then there's 9 RSA computations to generate this thing and verify it. And so it's a simple idea, easy to integrate, no changes to the RSA code. We can just use it and throw it in and it works. And it turns out that it actually is useful because here's a whole bunch of early papers that need a solution for this problem. This is the reason that we started. This is one of my papers. We actually implemented this protocol. It was incorporated into the Tumblebit open source project. And then we also realized later that this protocol works for more than just RSA keys. And so it actually was adopted by, in these papers, which ended up getting into these products, which are for computing crypto keys in a distributed way. So the reason that I think we had so much success with this one, this was like very little work really for us. We just did a paper, put it out there. But the thing was fully specified. We had code that worked. It was very easy to integrate. All the pieces fell into place, and so it got adopted. Okay. So, if I was to put things on the spectrum of like what happened with them, we had this DNSSEC privacy project that we started. Integration here was very hard, especially because the system was a moving target. We had VRFs, which, were basically, when we started, were fairly unspecified. There were some implementations, but they were mostly wrong. Actually, they were insecure. So this was kind of filling a void that people needed. And so we actually saw a good amount of adoption. Even though the integration wasn't that easy, people just needed to be able to use this. And then with our public key certification paper, integration was super easy. You just add this on top of whatever system you have. You don't have to go into software libraries and change them. Just add something new, and it all works. And so we got a lot of adoption from that. Okay, so those are the results I wanted to talk about. I want to bring us back to sort of like what I started with in this presentation. I think something that we can do to encourage people, to encourage the adoption of our research is to really encourage specification. I don't see that that's something that's commonly thought of by academics. We do look for running code, we do look for open source software, and I think that's becoming more and more part of how we think about research. But I also think that the process of specification is pretty significant. I can tell you that with the VRF project, we did spend like months, thinking about the specification in every detail. How do we choose the nonce? How do we, deal with the one bit of ED25519 versus the P256 doesn't have that bit? So how do we deal with this in the two different specifications? There's a lot of work you have to do to actually specify something, and I think that for all of the work that I'm showing here, that was where we invested. Academic returns on that were very low, but tech transfer returns were high, so I think it would be great if we as a community could sort of reward that type of work. Another thing is that there's a lot of plotting that has to be done in order to deal with integration in systems, and so with NSEC 5, we had an initial NSEC 5 paper that we published at NDSS, then we had another paper that was published at a theory conference. The ECDSA paper, actually, with the VRF is still unpublished because no one will accept that paper because we already have a paper on NSEC 5. So, I think we need to sort of give people time to work on projects and think about them and do the second paper and the third paper and enjoy the second paper and the third paper as reviewers, because there's a lot of interesting things that happen from the first paper, for example, in the NSEC 5 case, which was just RSA, to the second paper, the third paper, which was ECDSA plus this VRF, and then all this other stuff happened on top of that, right? So I really, since I got a soapbox, I want to use it to sort of talk about this, that I think we need to give ourselves time and years to work on these problems and see where they go and improve them to the point where people will actually use them. And yeah, so that's it. I'm really honored that I was here and able to tell you about this work and the successes and failures, and I'll be glad to take questions. Thank you.
Hello, my name is Jeff Mackey. I'm with the San Diego Supercomputer Center, and I was wondering how a VRF differs from a PGP signature.
Can you say that again? I didn't understand.
How does a VRF differ from a PGP signature?
From a regular signature? Yep. Well, it's a good question. So VRFs are sometimes even actually signatures. So I have a slide that I didn't bring here today, but let me see if I can do it without it. Yeah, it's this. So one way to actually think about, if you actually think about an RSA, the RSA version of a VRF, let me tell you how it works. Okay, if you were to do this with RSA, here's what you would do. You would take this input, you would produce an RSA signature. Okay, the proof is an RSA signature, right? And then the hash is just like a SHA-256 hash of the RSA signature. That's VRF constructed from RSA. I just showed you the construction. That's actually in our spec. And that's what we used in the first NSEC 5. So the proof is a signature, and the hash here is just a hash computed on the proof. So the thing that's special about a VRF is this property of uniqueness, right? So it is not the case. Think about an ECDSA signature. In ECDSA signature, there is not a one-to-one mapping between the message and the signature. If you know how ECDSA works, it uses a nonce. There can be many signatures for a particular message. So there is no uniqueness property. Okay? So the difference between a VRF and a signature is you can construct a VRF from a signature, but you need the signature to have a uniqueness property. RSA actually has that uniqueness property, but ECDSA does not. And so that's why we had to go with this complicated ECDSA construction, because signatures just don't work here. ECDSA signatures are not unique. So really, the answer to your question is that the difference is really uniqueness. We need this uniqueness property, which is not something we require of signatures.
Thank you.
NRA, Apple. Thank you for the talk, super interesting. I have a question on the, you stated that two metrics for InfoSec research should be ease of integration and, say, level or scrutiny of specification. Yeah. Can you elaborate on how to measure ease of integration?
Yeah, I don't think I can. I don't think it's something measurable, but I mean, I think for me in my career, one thing that I've always thought about is backwards compatibility, like how backwards compatible is a solution. I used to talk about this in terms of backwards compatibility, but I think it's more than that now. So I think, as a community, I think we're good at thinking about backwards compatibility for solutions, but I think there's more. And what I was trying to talk about in this talk was actually like the moving target nature of some of these systems. Like, we kind of look at the system and we say it's backwards compatible with the part of the system that we can see, but there's also like other parts that are changing and evolving as we're doing the research, or out of our sight, like we don't know that this is happening. And so, what integration means to me is like letting people like publish a paper, shop the idea around, and then come back and be like, okay, this didn't work for these 3 reasons, right? And now I have to fix all these things, and here's a new approach. It's completely different, and like everything I did before is wrong, And so I don't think that we give enough space for that. In our community, and I personally have struggled with that because I'm constantly in this situation where I'm writing like the 3rd and 4th paper, and like I can't convince anyone that there's anything in this paper that's worth looking at. I think that's where I'm trying to go with this. I don't know that I have a metric, but I think just giving people the space to like come back with feedback from the community and try again. See that it didn't work for this reason. Let's try again.
Thank you.
René Meyerhofer from Johannes Kepler University in Linz, Austria. First of all, thanks a lot for your intro on VRFs. My PhD student last year got excited about VRFs and data structures, and now I understand why. Thanks for that. My question is, agreeing with specification being very important, how do you actually fund that? We have gotten into some ISO standardization working groups, and I find it very hard to fund travel to those ISO meetings using the existing grant schemes because they don't typically have a category for that.
Yeah, so I've actually thought about that a little bit. So here's a strategy that I've used, and I've never done ISO, but I've done IETF for a while. So I have a talk that I gave at the IETF a couple years ago, actually, about this exact topic. My strategy is typically to go once or twice with the idea and try to find people that are regular goers to that standards body to buy into your idea. And then what you essentially do is you make them co-authors on the work, and you have them walk it through the standards process, because the standards process is extremely difficult and extremely slow. Even for me, I mean, the funding hasn't been a problem, but the time is a big problem. Like, you really need to invest in like constant attending these things. So I have 2 ideas. The first idea is, in the papers, include the spec as best you can, and the reviewers should judge the spec as a product, a work product that is worth, supporting for the work, right? So it's not just did you write the code, but also did you do the spec? You did the spec, great. That's another check mark for you as like a solid research paper. The second thing would be take the spec and bring it to the place where you need to bring it. And that process usually works for me if you just go once or twice by yourself and try to convince people that there's something here. You can usually get someone who probably is a stranger to you and is not a co-author, like a complete stranger, to join into the project and have them run the process for you so that you don't have to be the one attending and paying and going to all the trips and all that stuff. And so that actually worked pretty well for DNS, the DNS work that we had, but we did really hit a lot of hurdles that were real hurdles. And the VRF work has been picked up by the Crypto Forum Research Group, and so like that group has also been contributing to that development as well. So it hasn't only been us trying to push it. The other thing that I suggested in my talk at the IETF was when you go to propose something, don't put all your co-authors on the proposal. This is a weird thing to say, but I think it's really important. Do not put you and your 17 co-authors as the authors of the draft. The reason is because you want to get a bunch of people you don't know yet to be authors of the draft. You can only fit like 5 people as authors. So there's this constrained amount of people that can author a draft. So I really strongly recommend like doing 1 or 2 of the originators of the work as authors, and then try to get a whole bunch of other authors that are not you to be part of the draft and let them push the draft for you. And that's sort of the way you can get through the process with minimal time spent by the academics and more time by the standards folks, people whose job it is to be there at every meeting.
Thanks.
Hui Ling from the University of Nevada, Reno. My question is just, what is a weak collision property of the VRF?
I'm sorry, what is that?
The weak collision, because you read about randomness and collision property. What about the weak collision, like the Achilles hash for the birthday attacks, this type of properties?
Weak collision resistance. So you're saying I haven't talked too much about collision resistance in any of the descriptions that I gave. I just ignored that, which is true. I did. Okay, so let me just go here. Yeah, I mean, I don't know how well I can answer this question right now, other than to say that like a lot of the schemes that we proposed would break down if we had collision resistance. The reason that we don't, if we had collisions, the reason that we don't have collisions again is because if this hash function doesn't have collisions in this scheme, if this doesn't have collisions, there's uniqueness. We have only one way to get to this value over here, and then we take this value over here and hash it, and if this doesn't have collisions, then we won't have collisions in our VRF. So that's why we get the collision property here. It follows from no collisions here, no collisions here, and no collisions there. So we need to sort of follow it through. In terms of actually where we use the collision resistance property, it's pretty interesting because it often doesn't get used as much as you'd think. So for instance, in this case, the reason that we need collision resistance is so that we can't have two items that claim to be part of the data structure when only one of them is, right? So we're just using collision resistance in the basic way. And I can go offline if there's more details for that question that I didn't yet answer.
Other questions, comments? If not, let's thank Sharon one more time.